In the previous video, we saw that electromagnetic waves interfere with each other. Two superimposed waves in phase will create an amplified wave, while two waves in antiphase will cancel each other out. But just how does wave interference occur in a solar cell? And more importantly, exactly how can destructive and constructive interference improve the performance of our solar cells? At the end of this video, we will be able to answer these questions. The different layers in a solar cell can cause interference. This figure shows a cross-section of the air, a Rayleigh film, and silicon. EI represents electric field of an electromagnetic wave incident under an angle theta I. ER1 through 3 are the reflections of EI. We briefly introduce a second line beam with the same angle of incidence. We can see that the reflection of this light beam will interfere with EI in point A. At this point, the two waves incident from the same light source will not have traveled the same distance. Rather, the two waves will exhibit a path length difference. At point G, both incident light beams have traveled equal distance from the source. The path length of wave 1 is indicated by the yellow line, while the wave 2 is indicated by orange. For convenience sake, we will collapse the incident waves. To find how the waves interfere, we need to look into the optical path length difference. Let's first look at wave 2. The wave propagates from A to B and from B to C. Its optical path length therefore equals the sum of AB and BC multiplied by the refractive index of the medium, N2. AB and BC both equal D, the thickness of the gray layer, over cosine theta T, the angle of transmission, yielding the shown equation. The optical path length of the wave 1 simply equals the refractive index N1 multiplied by the distance CD. It follows from the geometrical relations that CD equals AC times the sine of theta I. AC in turn equals 2 times D multiplied by the tangent of theta T. Therefore, we can rewrite CD in terms of the angles of transmission and incidence and the thickness of the Rayleigh film. According to Snell's law, we can replace N1 sinus theta I by N2 sinus theta T so that the optical path length 1 and 2 are both expressed as a function of the same variables. The optical path length difference between the two waves can now be calculated by subtracting one from another. Through geometrical relations, we obtain a phase shift of 2 times the product of the thickness and refractive index of the Rayleigh film multiplied by the cosine of theta T. The total reflected electric field strength of an incident wave is equal to the sum of the electric field strengths of all reflection events. It can therefore be described by the reflected wave of the 1-2 interface plus the sum of all reflections at the 2-3 interface that are transmitted at the 1-2 interface. The reflected wave can therefore be described by a single wave function consisting of two parts. The first part describes the initial reflection event. It is equal to the incident wave EI multiplied by the reflection coefficient of the 1-2 interface. Notice the 1 pi phase shift with respect to the incident wave. As discussed in the previous section, this phase shift occurs when a wave is reflected off the surface of a material with a higher refractive index than the one the wave was traveling through. The second part of the wave function describes the multiple reflections event at the 2-3 interface. R and T denote the various reflections and transmission coefficients as described by the Fresnel equations. M denotes the number of reflections at the 2-3 interface. The path length denoted by Z is adjusted by the optical path length difference. The optical path length difference is multiplied by m to account for the multiple reflection incidents. Since all reflected waves undergo an even number of reflections, at a high refractive index interface they exhibit a 1 pi phase shift with respect to the incident wave. Constructive interference occurs for waves with a phase shift of 2 pi or multiple of 2 pi. Therefore, superimposed reflected waves will exhibit constructive interference if the phase shift equals 2 pi. The phase shift is equal to the wave number times the optical path length difference. From this relation, it follows that for waves of a certain wavelength to constructively interfere at normal incidence, the product of the thickness and refractive index of the layer have to match half the intended wavelength. Destructive interference occurs at a phase shift of an uneven number of pi's. When we can see that for normal incidence a 1 pi phase shift occurs when n times d equals 1/4 of the wavelength. The effect of introducing such a film with the optical thickness equal to 1/4 of the intended wavelength is shown in this figure. The wave reflected from the first interface and the wave reflected from the second interface are in antiphase. As a result, the total amplitude of the electric field of the outgoing wave is smaller, and therefore the total intensity, which is equal to the square of the electric field strength, coupled out of the system is smaller as well. As we discussed in the section of the Fresnel equations, the optimal refractive index for a Rayleigh film equals the geometric mean of the refractive indices of the encompassing media. Assuming the encompassing media are air and silicon, the optimal refractive index is around 2.1. Let's say we want to optimize the destructive interference for the 480 to 560 nanometer wavelength range, the spectral range in which the solar spectrum has the highest values for the spectral power density. We can now use the relation we found on the previous slide to calculate the optimal thickness. For optimal performance, the anti-reflection film thickness should be between 60 and 70 nanometer. Anti-reflection coatings are not the only way in which interference is used in solar cells. We will continue our discussion of the interference in the thin films in the next video.